The radiographic image is a result of X-ray photons in the primary beam interacting with different atoms in the body before reaching the image receptor. The X-ray photons may be transmitted, absorbed, or scattered in a new direction depending on the energy of the X-ray photon to begin with and the type of tissue the photons encounter. The photoelectric X-ray interaction with matter describes photon absorption at the atomic level. At the beginning of a photoelectric interaction, an incident X-ray photon enters the atom and transfers all of its energy to a K-shell electron. This energy transfer results in the ejection of the electron from its orbit. The ejected electron is called a photoelectron. This ionization event creates a vacancy in the K-shell of the atom. To restore its neutral charge, the atom fills the vacancy with an electron from its outer shells, usually the L shell. The atom continues to stabilize itself by having an electron from the M shell fill the vacancy left in the L shell vacancy until all of the shells are once again filled. This movement of electrons is termed a characteristic cascade, or a cascade effect, and is essentially the same process that occurs during characteristic X-ray photon production. To satisfy the law of conservation of energy, a characteristic X-ray photon emerges which is equal to the difference between the two electron shell binding energies. It is important to note that due to the low energies of the photons produced in this manner, few, if any, of these photons are able to exit the patient. Photoelectric interactions are more likely to occur in bone compared to other tissues in the body because of its relatively high density and atomic number. This is why all bony tissue in radiographs appear white. The X-ray photon is completely absorbed by the bone and is therefore unable to reach the image receptor.